Welcome to the Platform Engineering Playbook podcast, where everything you hear is built, reviewed, and improved by AI, by me, and by you, the listener. This show keeps me, and hopefully you, up to speed on the latest in platform engineering, SRE, DevOps, and production engineering. It's a living experiment in how AI can help us track, explain, and discuss the fast-moving world of infrastructure. Every episode is open source. If you've got something to add, correct, or challenge, head to platform-engineering-playbook.com. You'll find all the content and a link to the GitHub repo. Open a pull request, join the conversation, and make the playbook smarter. Let's get into it.
Let's connect to what we covered. Pause and try to remember. In episode 2, what was the 5-minute RTO for Hotworm? And in episode 3, what was Aurora's typical replication lag? Take a second. 5 minutes RTO, 1 minute Aurora promotion, 4 minutes everything else. That, everything else? That's your Kubernetes layer, Aurora lag. 45 to 85 milliseconds normal, 1 to 30 seconds under load. Today you're learning how to implement that compute layer. Aurora gave you multi-region data. Kubernetes gives you multi-region compute. You need both for Hotworm. By the end of this lesson, you'll understand how to architect EKS clusters across regions without the operational nightmare most teams create. What you'll master today, why the EKS control plane is your regional boundary and what that means for design, independent clusters versus federated clusters, when to use each. Cross-cluster service discovery that actually works, hint, not Kubernetes Federation, and the service mesh approach that Netflix and Spotify use in production. Let's start with something most engineers miss. The EKS control plane is a regional service that depends on multiple availability zones, not multi-region. Regional. What does that mean? Your control plane, the brains of Kubernetes, lives in one region, US East 1 or US West 2, not both. Here's how it actually works. The EKS control plane is managed by AWS. It runs across 3 or more availability zones in a single region. The etcd cluster, that's your Kubernetes database, is distributed across those AZs using Raft consensus, needs a 2 of 3 quorum to function. The API server is load balanced across AZs in that region. Your worker nodes can be in the same region, different AZs. Why does this matter? If your control plane is in US East 1 and that region fails, you can't schedule new pods, you can't scale, you can't deploy. Your existing workloads keep running. The kubelet doesn't need the control plane for that, but you're in read-only mode. This is fundamentally different from Aurora. Remember episode 3? Aurora can fail over its primary across regions. Storage layer replicates. Control plane promotes. 90 seconds, and you're operational in the secondary region. EKS cannot do this. The control plane stays in its home region. It's tied to that region's infrastructure, the etcd cluster, the API servers, the networking. You cannot fail over an EKS control plane across regions. Picture this, 2 separate Kubernetes clusters. One control plane in US East 1, managing worker nodes in US East 1. Another control plane in US West 2, managing worker nodes in US West 2. They're independent, not talking to each other. This is by design. Here's the misconception engineers make. They think multi-region Kubernetes means one cluster spanning regions. Wrong. That's not how EKS works. You get multiple independent clusters, one per region. The control plane is your regional boundary. Accept this. Design around it. Now let's talk about how those clusters relate to each other. You've got 2 fundamental patterns, independent clusters and federated clusters. Independent clusters. This is what I recommend. 2 completely separate EKS clusters. One in US East 1, one in US West 2. Each has its own control plane, managed by EKS. Its own worker nodes. Its own deployments, services, config maps. Its own monitoring and logging. How do they coordinate? They don't coordinate at the Kubernetes level. They coordinate at the infrastructure level. Aurora Global Database replicates data between regions. We covered that in episode 3. DNS routes traffic using Route 53 with health checks. Service Mesh handles cross-cluster communication. We'll get to this. and your CI/CD deploys to both clusters. GitHub Actions, GitLab CI, whatever you use, it pushes the same manifests to both clusters. What are the advantages? Simplicity. Each cluster operates independently. Resilient. One cluster failure doesn't affect the other. Flexible. You can run different versions for blue-green deployments. No blast radius. A problem in one region stays contained. Remember episode 1? The hidden SPOFs in Route 53 and IAM that took down both regions during the October 2025 outage? This is why you want independent clusters. If they're too tightly coupled, a control plane failure affects both. Keep them independent. The alternative is federated clusters, and this mostly failed. Kubernetes Federation was the official approach years ago. One host cluster managing multiple member clusters. Automatically replicate resources across clusters. You deploy a deployment to the host, and it magically appears in all member clusters. It failed. Badly. Here's why. Complexity explosion. Debugging across federated clusters is a nightmare. Your pod is running in US East 1, but crashing in US West 2. Why? Different node configurations? Different secrets? Different timing? Good luck figuring it out. Eventual consistency issues. You update a config map in the host cluster. It takes 30 seconds to propagate to the member clusters. Your application in US West 2 crashes because it's reading stale configuration. This is not theoretical. This happened regularly. Limited adoption. Kubernetes Federation v1 was deprecated. Federation version 2, called KubeFed, never reached maturity. The Kubernetes Special Interest Group couldn't solve the fundamental complexity problem. And nobody uses it. Even Google, the creators of Kubernetes, doesn't recommend federation anymore. That should tell you something. What replaced it? Modern approaches, multi-cluster service mesh like Istio or Linkerd, GitOps with Argo CD or Flux deploying to multiple clusters, traffic management at the DNS or load balancer level, service discovery via external DNS. So when do you use what? Use independent clusters when you want operational simplicity. You can handle eventual consistency, and most applications can. You're implementing hot-warm or hot-cold patterns. You want blast radius isolation. Consider federation alternatives, specifically service mesh, when you need automatic failover at the service level. You have active traffic requirements. Your Netflix scale with dedicated platform teams. And you can handle the operational complexity. For most teams, independent clusters with GitOps. Deploy the same manifests to both regions. Use DNS for traffic routing. Keep it simple. Now here's the problem that trips up everyone. Service discovery. Your front-end pods in US East 1 need to call your API service. Where is that API? In normal load, US East 1. During failover, US West 2. How do pods discover this? In a single cluster, you'd use Kubernetes Service Discovery. The API service has a DNS name like !api.default.svc.cluster.local. Pods resolve that. Connect to the service, it load balances to pods. Simple. But that's cluster local. It doesn't work across clusters. !api.default.svc.cluster.local in US East 1 only knows about pods in US East 1. It has no idea about US West 2. Solution 1. External DNS. This is the simplest approach. Use DNS, not Kubernetes Service Discovery. Your API service is !api.yourapp.com, not !api.default.svc.cluster.local, Route 53 health checks monitor US East 1 API endpoints. On failure, Route 53 updates DNS to point to US West 2. Your pods resolve !api.yourapp.com and get the current region. How to implement 1. Each cluster exposes services via load balancer or ingress. 2. External DNS controller watches Kubernetes services and creates Route 53 records automatically. 3. Health checks monitor each region's endpoints. 4. DNS-TTL is 60 seconds. That's the trade-off between failover speed and caching. 5. Pods use DNS names, not cluster local service names. Your frontend doesn't connect to _API.default.svc.cluster.local. It connects to _API.yourapp.com. Advantages? Simple. Works with any Kubernetes distribution. No special setup. Standard DNS resolution. You already know how DNS works. Limitations? DNS caching. 60-second TTL means up to 60 seconds to detect failover. Pods might have longer cached values depending on their DNS client. No automatic retry logic. Your application must handle DNS resolution. And Route 53 failure affects all regions. Remember Episode 1's hidden SPOFs? Solution 2? Service mesh. This is production grade, but operationally heavier. Istio, Linkerd, or Console Connect. You install sidecar proxies on every pod. A service mesh control plane runs in each cluster. Multi-cluster mesh configuration connects the control planes. Services in US East 1 can discover services in US West 2 automatically. Here's how it works. Install Istio in both clusters. Configure multi-cluster mesh with a shared root certificate. This is for MTLS security. Services in US East 1 can now discover services in US West 2 through the mesh. Envoy proxies, those sidecars, handle intelligent routing. They prefer local endpoints. If your frontend in US East 1 calls the API, Envoy routes to API pods in US East 1 first. Lower latency, same cluster. But if the API pods in US East 1 start failing, Envoy detects this. Circuit breaker trips. It automatically fails over to API pods in US West 2. No DNS wait, no application-level retry logic needed. The mesh handles it. You get automatic retries, circuit breaking, timeout handling, and telemetry. You can see cross-cluster traffic flows in your observability tools. Advantages? Automatic failover with no DNS delays. Intelligent routing that's latency-aware and locality-weighted. Observability with distributed tracing across clusters. Security with MTLS between all services. Limitations? Complexity. Service mesh is operationally heavy. You're managing the mesh control plane, sidecar injections, certificate rotation, version upgrades. Performance overhead. Sidecar proxies add latency, typically 2 to 5 milliseconds per hop. Learning curve. Istio is notoriously complex. Resource cost. Every pod gets a sidecar proxy. That's more memory and CPU. Let me show you a real production example. E-commerce company running hot warm. Primary cluster in US East 1 serves 95% of traffic. Secondary cluster in US West 2 at 20% capacity, ready to scale. They use Istio service mesh with multi-cluster configuration. Front-end to API calls, prefer local, failover to remote. During a US East 1 failure, let's say the entire region goes down at 2 p.m. on Black Friday. Envoy sidecars detect API failures in US East 1. Health checks fail. Circuit breakers trip. Envoy automatically routes to US West 2 API. No DNS wait. Traffic shifts immediately. EKS autoscaling in US West 2 brings the cluster from 20% to full capacity. Pod schedule, scale up, ready in about 2 minutes. Total failover time, 2 minutes. That's way faster than the 5-minute DNS approach. But they're paying for it. Operational complexity of running Istio, sidecar resource overhead, dedicated engineer just for mesh operations. Is it worth it? For them, yes. They're processing $200,000 per hour during peak. 2 minutes versus 5 minutes saves them $10,000 per outage. The Istio complexity cost is justified. For a smaller company doing $10,000 per hour? Probably not worth it. DNS-based failover is fine. Now let's talk about why Kubernetes Federation failed. Because the lessons matter. Federation promised automatic resource replication. Deploy once, runs everywhere. Reality was different. Debugging hell. A pod fails in one cluster but not another. Why? Different node instance types? Different kernel versions? Different timing on secret propagation? You'd spend hours tracking down why the same manifest worked in one cluster and failed in another. Eventual consistency nightmares. You update a config map in cluster A. It takes 30 seconds to propagate to cluster B. Your app crashes in cluster B because it's reading stale config. Then, the update arrives. App recovers. But you've got 30 seconds of downtime and no clear indication of what went wrong. Limited resource support. Federation v1 only supported basic resources. Deployments, services. No CRDs. No stateful sets initially. Your modern Kubernetes usage doesn't work with Federation. Community abandonment. The Kubernetes SIG multi-cluster gave up. They deprecated Federation version 1. Federation v2, KubeFed, never reached stable. The community couldn't solve the fundamental problem. Managing multiple clusters as one is too complex. What actually works? GitOps, Argo, CD, or Flux. You have one Git repository with your Kubernetes manifests. Argo CD watches that repo. When you commit a change, Argo CD deploys to both US East 1 and US West 2 clusters. You control what goes where, not automatic replication, explicit, declarative configuration per cluster. If you need different configurations per cluster, you use customize overlays or Helm values. Clear, explicit, debuggable, lesson learned. Don't try to make Kubernetes do multi-region at the control plane level. Keep clusters independent. Coordinate at the infrastructure and application level. Let's talk about common mistakes, because I've seen these kill projects. Mistake 1. Trying to span regions with one cluster. Engineers add worker nodes in US West 2 to a control plane in US East 1. It technically works. But why does it fail? High latency. Pods in US West 2 talking to the control plane in US East 1 over a cross-region network. Slower API responses. Cross-region network costs. And the control plane is still single region. If US East 1 fails, your US West 2 nodes are orphaned. Fix. Accept the EKS boundary. Use independent clusters. Mistake 2. Overcoupling clusters. Synchronizing everything in real time between clusters. Every config map, every secret, every service. This creates dependencies. A problem in one region cascades. Blast radius across regions. Fix. Embrace eventual consistency. Coordinate only what's necessary. Most applications can handle a few seconds of configuration lag. Mistake 3. Forgetting the control plane dependency. Engineers assume existing pods keep running during region failure. That's true. Pods don't need the control plane to run. But you can't scale, can't redeploy, can't heal. If a pod crashes, the kubelet tries to restart it. But if the node dies, you can't schedule a new pod. Your cluster is effectively frozen. Fix. Design for immutable, long-lived pods with proper health checks. Or accept that you'll fail over to the other region when the control plane is down. Before we wrap up, pause and answer these questions. Question 1. Why can't you fail over an EKS control plane across regions like you can with Aurora? Question 2. What's the main reason Kubernetes Federation failed? Question 3. You're implementing hot-warm. Do you use external DNS or service mesh for cross-cluster discovery? Think about the trade-offs. Take a moment. Answers. Question 1. The EKS control plane is a regional service running in 3 AZs within one region. It depends on that region's infrastructure, etcd, API servers, networking. Aurora separates compute from storage. The storage layer can replicate across regions and promote. But EKS can't separate the control plane from its region. It's fundamentally tied to that region's availability zones. Question 2. Federation was too complex operationally. Debugging failures across clusters was impossible. You'd have the same manifest working in one cluster and failing in another with no clear reason why. Eventual consistency caused subtle bugs, config maps propagating late, applications crashing. The community couldn't solve the fundamental complexity problem. Even Google stopped recommending it. Question 3. Hot warm with 5-minute RTO. External DNS is simpler. 60-second DNS TTL is acceptable. Hot warm with sub-second failover requirement? Service mesh, but only if you have the operational maturity to run Istio or linkered. Don't add service mesh complexity unless you need it. Let's recap what we covered. First, the EKS control plane is regional, not multi-region. It runs in 3 availability zones within one region. This is your boundary. You cannot move it. Design around it. Second, independent clusters are the right pattern for most teams. 1 cluster per region. Coordinate at the infrastructure level. Aurora for data, DNS for traffic, CI/CD for deployments. Third, Kubernetes Federation failed. Don't use it. Use GitOps with Argo CD or Flux. Or use Service Mesh for advanced use cases. But not Federation. Fourth, cross-cluster service discovery has 2 approaches. External DNS for simplicity. Service Mesh for automatic failover and intelligent routing. Choose based on your operational maturity and RTO requirements. Fifth, Service Mesh like Istio or linkered provides automatic failover but adds operational complexity. Every pod gets a sidecar proxy. More memory, more CPU, more management overhead. Only use if you need the capabilities. Remember episode 2? The hot-warm pattern with a 5-minute RTO? Now you know how to implement the compute layer. Aurora Global Database from episode 3. Data layer, 1-minute failover. EKS clusters from today. Compute layer, 2 to 4 minutes to scale and route. Together, your 5-minute RTO hot-warm architecture. This independent cluster pattern is what we'll build on in episode 11 when we cover advanced multi-region Kubernetes patterns. And in episode 12, we'll walk through the actual failover procedure using these clusters. Next time, network architecture, transit gateway, VPC peering, private link. You've got Aurora replicating data. You've got EKS clusters in multiple regions. How do they communicate? You'll learn when to use transit gateway versus VPC peering and why transit gateway scales. Private link for secure cross-region service access. How to design network topology that doesn't create hidden bottlenecks. And the network layer mistakes that killed multi-region projects. Because clusters don't talk to each other via magic. They talk via VPCs, subnets, and routing tables. Get this wrong, and your whole architecture breaks. See you in episode 5.
That's it for this episode of the Platform Engineering Playbook podcast. Every topic, transcript, and summary you just heard lives out in the open at platform-engineering-playbook.com, where anyone can suggest updates or add insights through GitHub. If you've got thoughts, fixes, or new ideas, open a PR. And if you enjoyed the episode, rate us on your favorite podcast platform. We're always shooting for 5 stars. While you're there, give the project a star on GitHub. It helps others find and contribute to the Platform Engineering Playbook. This podcast is generated by AI, reviewed by AI, me and you, a community of engineers keeping our craft sharp. Thanks for listening, and see you next time inside the Platform Engineering Playbook.